So it's my pleasure to introduce Professor Vicky Mak-Hau from Deakin's School of IT. She's a professor in optimization, has worked in lots of different optimization applications and from the very theoretical to the very practical. And today she's going to talk to us about satellite management. So take it away.
Okay, thanks, Peter. Hold on a second, I seem to be hearing some feedback. Are you guys hearing me okay?
Just give me 1 second and I'll make sure that
we're hearing you without feedback.
Yeah.
Okay, all right. I don't know why I'm hearing some feedback, but anyways, okay. All right, so I'll start. Thanks, Peter, and thanks, Optima, for the opportunity for me to present our work in the last 2 or 3 years. So it is about dynamic resource management for GEO high-throughput satellites. So this is my team. We've got 3 PhD students working with me. So Mak-Hau is working on some other SATCOM problems. And Ryan and Angus are the people who have been working with me on this project. We have Trudy as a postdoc, and Alvaro just joined us as a casual researcher maybe a few weeks ago. So, sorry, I need to reset my earphone. Can you guys still hear me?
Yes, we can.
Okay, all right. So, all right, so the SATCOM, it is all about transmission of signals, and so we have, we have links, so uplink and downlink. So when one terminal wanted to communicate with another terminal, we have a link. So the uplink terminal, it could be a ground station, or it could be a user. A user could be on the ground, it could be at sea, it could be in the air. And similarly for the downlink terminal. And there are many topologies. So they have things like the star topology, or hub and spoke, or mesh and broadcast, and all the rest of it. So it could be quite complicated already. And we also have other things that make it even more complicated. So we essentially have to make a lot of decisions at the same time. So we call it everything everywhere all at once kind of problem. But it is a lot of fun. So now about the decisions we need to make. So we call it decision variables. This is only the first slide that describes the decision variables. So from the uplink side, we have the transmit power that we can adjust or optimize. And then we have the frequency, the bandwidth, the power together with the gain will give you the EIRP. And then when the signal is transmitted to the satellite, there's the losses. So we have the pointing loss, atmospheric loss, implementation loss, and a lot of other losses as well. And the free space path loss depends on the transmission distance and also the wavelength, but the wavelength depends on the frequency. And then the EIRP limits your power. And there's also another thing called SPFD, which is the spectral power flux density, which is also banded, and that limits your EIRP, and it also depends on the bandwidth. So that's some more thing that you have to take into consideration. And then at the receiving antenna, you have the gain or noise temperature ratio. And then there are some more gains and losses on the satellite. And then in terms of decision variables, we can optimize the receiver gain, we can optimize the HPA gain, we can optimize the downlink subchannel gain. And then the downlink frequencies can also be a decision variable. And then you have more losses and interference. So it is all about being able to close as many links as possible. And we need to meet the link margin requirement, and the link margin depends on the carrier loss ratio, the uplink and downlink composite carrier loss ratio that gives you the EBNO. So the link margin is the difference between the achieved EBNO and the required EBNO. So if that is not horrible already enough, and we also have the beam footprints that you can optimize. So that would be the let and long of the center of the beam that we can, we can place the beam, in a particular location, and also with the width of the beam that you can adjust. So that's two decisions already, and then you can optimize the beam's receiver gain, and also one of the hardest things is the user beam allocation. And you can also determine the color of the beam. By color, we mean the frequency reuse. So this is a downlink beam footprint. So I thought I'll just show you two different diagrams. So for today, there are actually many optimization problems. So we're working on, I think maybe 4 or 5 at the moment. But what I wanted to present today is the work we've been doing for FlexBeamOpt. So that's the one that optimizes the beam footprints, the frequency reuse, which is the coloring part, and also the user to beam allocation. So before I do that, I'm just going to stop sharing this for a minute and show you something. So this is our Australian's NBN CO1B. I think that's what the satellite called. So these are what their beam footprint look like. So they are tessellated, something like this. So they've got 2 different beam sizes, the small ones and the wider ones. The SCIS 17 has got this kind of footprint. So again, they are tessellated. But so here's another example. But if we are able to place our beams like this, it will be more flexible and also a better use of the resources. So in this diagram, the beams that we've been using has got a beam width of between 0.3 degrees to 0.6 degrees. And so this is an instance for Australia. I sort of have something else I wanted to say about this. Anyways, so about beam footprints. So this is what I wanted to say. So it's not like we have a real border for the beam footprints, but these borders are the 3 dB, minus 3 dB mask. So they call it the half power beam width. And then we define something for the beam planning region. So because we needed to capture the beams that are neighboring each other and avoid using the same color for beams that are neighboring each other to avoid interference. The beam planning region, we were using something like a minus 25 dB. So that will be probably around about here. So the minus 3 dB is around about here. So the width is about, the width for the beam planning region is about 1.58 times of the half power beam width. So that I'm talking about the main lobe here. And then you have a lot of side lobes. So even though you're very far away from this red beam, for example, when you have another red beam here, there may still be some kind of interference, but so we hope that it's going to be up to date. So here's another example for European, the one instance, European instance. So we have the uplink and downlink beams. So you don't have to worry about the uplink and downlink beams interfering with each other because they're using completely different frequency bandwidths. But you do have to worry about beams of the same color if you don't want to place them too close to each other. The 3 white beams here are covering 3 gateways, and we want to allocate. I think in this case, we allocated 4 colors to these gateways. But when you have users that are close to the gateways, you probably want to do something smart about it, because if the gateways are already using all 4 colors and you have a beam that needs to use one of the colors, then you may have interference, but we have figured out a way to deal with problems like this. So about the bands, you probably have already heard about the KA bands, KU bands, and X band, and that sort of thing. So for the two examples I showed you earlier, the SCS-17 and the NBN satellites, they are using KA band. So those have got a bandwidth of 26 to 40 gigahertz. So now, before I talk about the mass, just a overview of the methodologies that we have tested. So our first paper are about these three methods, the FlexBeamOpt, version 1 and 2 and 3. So I just call them FBO 1 and 2 and 3. The first one is actually our most favorite algorithm because we used integer programming for some part of the problem and then constraint programming for some other part of the problem, weighted k-means, Mak-Hau, and some custom heuristic. So we call it a bit of this and a bit of that algorithm, so a bubble. And then the second method is one where we generate some candidate beams and use integer programming to select a few beams out of those candidate beams. So this is almost like streaming column generation to us. So we decided to use pricing. And I saw that it would not be cool to be standing here presenting, but not mentioning anything about either column generation or branching cut and price or Lagrangian relaxation or density decomposition or density Wolf decomposition. So I thought we have to do something. So we did column generation. So before I talk about the math, I'll probably show you the results first, because that's what people normally do when they review a paper, just go straight to the results. We generated 12 problem instances. I know that if we have some machine learning experts sitting here, they're probably already screening, how can you only have 12 instances? But because we built the algorithms from scratch and wanted to have a view of how they behave when we have fewer users, like the 500 users, and more users, like the 5,000 users, and we have some realistic cases, random user distribution cases, and also the clustered distribution instances. So we thought 12 is enough, but it's an ongoing experiment where we'll generate more instances in the future to test our algorithms. So anyways, so here are the 12 instances. So we have the 500 user instances and the 5,000 user instances. 11 and 12 are the hardest to solve because they are, the user distributions are clustered and we are talking about 5,000 users. Particularly 12, we are talking about the demands distribution in a random demand distribution. So this is the hardest problem to solve. So back to the different algorithms we've tried. So the first three, the blue, red, and black, they are the ones that we tested in the first paper, so including the abort algorithm. So we can see improvements in the algorithm that we developed in the second paper. But the yellow one, which is one that is exhaustive-ish kind of algorithm, we only managed to solve 4 problem instances. And that is a good reason why, because it just takes too long and out of memory as well. But at least the good thing is, for some instances, we can see that our column generation kind of approach is not doing too poorly compared with the yellow bar that you can see here. So they are actually quite close in terms of the percentage demand being met. It was, of course, going to be the ones taking most of the time. The column generation ones are not too bad, particularly the one that we truncated them into just 500 beams. I'll explain that later. But every algorithm has its good and bad about it. For example, FBO3 is the one that gives us most of the time not so very good percentage demand met. Particularly if you look at the 5,000 user cases, but it is the fastest. So even for the most difficult problem, it's taking less than 100 seconds. So if we need frequently, like rapid optimization, probably FBO3 is not a that idea. But if you have loads of time, so then you can just implement CG plus 500 or linear. These are two of the better algorithms in the second lot of the algorithms that we tested. So here is a two-dimensional representation of the outcome. So it's easier to see the trade-off between spending more computation time and having a better percentage demand met. So these are the 5,000 user instances, and these are the 500 user instances. So you can see that the red dots, I'll just explain what they are. The blue dots and the orange are from the first three algorithms, the FlexBeamOpt, so FBO1 and 2, 3. The blue ones are the virtual mean time algorithms. So we take, for each instance, we take the algorithm that took the shortest amount of time. Most of the time it is FBO3, except for 2 instances. The orange dots are the virtual max demand algorithm out of the first 3. So whichever is the one that produced the best percentage demand met. And then the red are from CG plus 500, and the green ones are from IPMIA. IPMIA actually did better than the red one in one problem instance, which is 9. So I thought there's still a point presenting it. So these are the results for the realistic user distribution instances, and it's very similar to the random user distribution instances. But for these ones, you can see some clear improvements, or even for IPMIA compared with the first 2 algorithms. And the improvement is more clear, even for the clustered user is the 5,000 user instances. For instance, 11 and 12, IPMIA did much better than the FlexBeamOpt 1, 2, 3. And we also experiment with the different frequency reuse scheme. So if you remember, I mentioned about colors earlier. The colors are, so that we call a beam a channel. And then, so for a 4-color scheme, and if we have polarization, for example, so we could chop the beam into 2, the bandwidth into 2, and then with polarization, so then we get 4 colors. That there will still probably be a small amount of interference for the same frequency, even if you're having using different polarization, but that's a very small amount, I was told. But so we can have 4-color scheme, 6-color scheme, 8-color scheme, or 3-color scheme. Now, this is where I think machine learning can help, because it is very hard to make a conclusion from these results, because, for example, the 8-color scheme, it is the slowest in some problem instances, but it is one of the faster ones. It didn't do too well in terms of demand met, but in general, overall, it is not too bad. Some of the other color schemes, they are, the winner in some instances, but they did really poorly in other instances. So I guess probably if we study the future of the, for example, like the distribution of users and distribution of the demands and all the rest of it, and plug it into a machine learning algorithm, for example, it could probably tell us, what is the best method to use, and also what is the best frequency reuse scheme to use. So that's we need to leave it for future research. So now, finally, the math. So let's go back to this diagram where we have an instance, Australian instance. I think this is one of the 500 user instances. So all the black dots are the demand points, but they do have a random demand generated. So now, when we started with the project, we have absolutely no clue where to even start. And then one day, I can't remember who found this paper, Camino et al.'s paper, published in 2021. It's probably one of the PhD students. And then from the integer programming model presented in the paper, we figured out, what the problem is. And then, so then we developed all our other algorithm and all the rest of it. So it is a very good paper. So if you, like to read it, I'll send you the link. Anyway, so they presented an integer programming model, and then we have made some small modifications to it, but in basically more of to try and understand what the problem is. So you have the first constraint here is saying each user can only be served by a beam. A user could be covered by many beams, but it should only be routed to one beam. So it can be routed to two beams. And then we have the beam width. So if we do have a beam active, then it should be given a width, beam width, and it should be between some limits. And then, so users served by a beam has to be inside the -3 dB footprint, so half power beam width footprint. So if it is outside of the half power beam width, then we will not allocate the user to the beam. And then I think they used Euclidean distances. So we saw it's probably cool to use a half a sine distance. Not that we are really going to solve it inside of the integer programming problem. And then the next lot of constraints are to do with the coloring part. So we have a lot of logic constraint to capture the fact that if we have two beams being colored the same color, it's going to be given one for beta B, B dash. And then we use this constraint here to ensure that if there are two beams and colored with the same color, they should be at least a certain distance away. And then we have some cardinality constraint and a NASAP constraint. So I'm going to talk a little bit more about the NASAP constraint later on. So that's to capture the beam capacity, which has an chicken and egg kind of property. So if you read the literature, most people use this sort of objective function to minimize the unmet data rate or the differences, absolute difference between the data rate, the required and the achieved data rate, or a ratio of achieved and the required data rate. And I thought, so, for us, because we just want something, easy to capture, so we used a surrogate objective function where we just use the requested data rate and try to maximize it. So instead of minimizing amount of demand, we're just going to maximize the demand being covered. And then we thought, given that we were, the model that we're seeing now is actually a nonlinear programming, integer programming model. Of course, it's going to be hard to solve. So why don't we make some decisions first? So that naturally we think about, the kind of decision we're going to make is we just have the beam laydown plan done. So, so I'm talking about we decide the location of the beams, where we place them, what the widths are. So after making that kind of decision, we would know which beams are active, which beams are not active. So we don't need this constraint anymore. And then all of these are going to be known already. So we suddenly have, a lot less decision variables. And also we don't need this constraint anymore, because this is just one that says, a user can only be routed to a beam if it's in, within the 3 dB beam footprint. So, and then after that, we suddenly have a blue problem and a green problem. So the blue problem is actually the user to beam allocation problem. And it is an optimization problem, because we do have the decision variables in the objective function. The green problem does not have the decision variable in the objective function, not really related to any of the other constraints in here. So it is actually just a constraint programming problem, really a coloring problem. So the blue problem, so here's just another slide. So it has got a simple set packing constraint, and it has got two sets of cardinality constraint and a NASAP constraint. Now, so remember I mentioned earlier that the NASAP constraint is a bit of a chicken and egg constraint. And the reason that it is a chicken and egg constraint is because the capacity of the beam is something that we wanted to capture about the carrier noise ratio. the carrier power is okay, but the noise power is a bit of a problem here because we want to take into consideration the user with the worst performing antenna and how far they are away from the center of the beam. But before we know which are the users being allocated the beam, of course, we won't know that. So, but that's the whole purpose of this optimization problem. We're trying to allocate users to the beam. So we have to make some assumptions, but of course the problem is if our assumptions are too conservative, you're going to miss a lot of the good solutions. But if the assumptions are too loose, then we're going to have infeasibility in the sense that we can't close some of the links. So, and because of that, we actually came up with all the other algorithms that we developed. But I still want to talk a little bit more about it because that's our most favorite bot-to-bot algorithm. So as I mentioned before, so this is a flow chart of the algorithm. So in the beginning, we do some initial beam laydown. So we tested two algorithms. The first one is the weighted k-means just to do the clustering. I know that there are better, newer algorithms to do clustering, but at the time we just thought, oh, we should quickly pick one and then implement it. And then we implemented our own feasibility repair and improvement algorithms. And then we have the moving centroid heuristic algorithm. We call it Mak-Hau because everybody likes coffee in my team. So we call it Mak-Hau. And that one, we don't have to do the feasibility repair and improvement. And then we solve the integer linear programming problem for the CCKP, so the user to beam allocation optimization problem. Oh, I forgot to talk about domain adjustment. So remember this diagram that I mentioned earlier, we have the main lobe and side lobe and all the rest of it. So if I have a user and I've got three options here allocated either to the blue beam or the red or the orange beam. So because it is very close to the center of the blue beam, you don't have to adjust the demand very much. But if you allocate it, so route it to the red beam, you're going to multiply the demand by a number larger than 1. So the further away it is, the larger the number you want to use to capture the fact that you have a reduction in terms of the signal gain, because it's very far away from the center of the main lobe. And then we do a few of the other things. So after we've done the beam laydown, and sometimes we will, after we've done some repairing, improvement, heuristic, we will have some beams freed up, and then we just try to allocate those beams to other places by using Mak-Hau. And then we'll do beam coloring, which we are solving an integer linear programming problem to minimize the loss of the load. And then we do some, remove some beams due to excess colors. I'll explain that later. And then we may have some freed beams again. Then we use Mak-Hau to allocate those beams and also use constraint programming to tell us, oh, can I still color these beams with 4 colors, for example? And then at the end, we solve an integer linear programming problem again to re-optimize the user to beam allocation and do the power allocation. So you have seen this ILP before, so I'm not going to explain again. The mean loss coloring is using this integer linear programming problem, but you can also just do max coverage coloring. So it's the same thing. So that's our bot-to-bot algorithm, which we really like. And then our second algorithm is about selecting from a set of candidate beams and then using integer programming model to select the best beams out of the candidate beams. So say, for example, if we run our eMak-Hau, we actually have another version of Mak-Hau called eMak-Hau, which stands for exhaustive Mak-Hau. It will make sure every single user is in a beam. So for example, the SAS-17 has got 200 spot beams. So let's assume this NB equals to 200. And by running a single run of eMak-Hau, we end up with 375 beams, for example. Then we solve this integer linear programming problem to choose 200 out of the 250 beams, 25 beams, the one that gives you the best demand. And then the next two constraints are to do with colors. As I said before, the beams, neighboring beams cannot be used in the same color. And then if we run eMARCA multiple times, we will have a user being covered by multiple candidate beams. Then we're going to add this constraint to make sure that each user will only be routed to at most one beam. And then we also have FlexBeamOpt version 3, which is a heuristic algorithm. So I thought it is best to explain the algorithm by using the pictures. So assuming we run eMARCA once, so then every user will be covered in a beam, but we can't have that many beams, of course. So first of all, we need to fix the coloring problem. So say, for example, we have a 4-color system, then we're just going to convert this into a graph and find the cliques in the graph to see if we have any cliques of size 5 or above. And suppose the green ones are the one that we decided that they need to go, the green beams. So we remove them. And with this set of beams, we know that we are certain that we can color them with 4 colors. And then we're going to have to make a decision which beams do we want to remove further if we end up using more than the number of beams available on the system. So for example, I think in the paper we used the system with 72 beams. So if we have, say, for example, 80 beams here, you're going to find 8 beams to remove. But if you're using, for example, only 60 beams here, then you're using fewer beams. So that's a FBO3. I think I still have a bit of time. So, and then we thought it is just really not cool to not use any of the cool integer programming algorithms. So we thought this is FBO2 is actually screaming column generation to us. So we did that. So every time when we generate a beam, it's like generating a column. So the columns are beams. And we actually just use pricing to help us find, which of the beams that we should add to the current set of collected beams. So exhaustive is a really, really boring algorithm. But the IGNIA is kind of cool because it has the evolutionary aspect of it. So I'll explain that in the next slide. So the exhaustive EMR, the exhaustive one is that we have the brute force Mak-Hau. So we run eMARCA once, and then we run it for the second time. And then hang on a second, this is, yeah. So we run eMARCA once, and then we run it for the second time. Of course, then this time we may have some beams that's being duplicated. So we have to remove the duplicated beams. And then we run it for another time, remove the duplicated beams, and it just go on forever. And then you can imagine, so it's going to take longer and longer to remove the duplicated beams. And then we do have a stopping criteria, of course. So if all the beams being generated in an iteration of the are not new, then we're just going to stop and then we solve the integer problem. So it's going to take a lot of time. So that's a EMR that only manages to solve 4 of the problem instances. And then we have IGNIA, which is completely the other end that is trying to not collect as many beams as possible. So what it does is that we run eMARCA once, and then say the system has 100 spot beams. So we run eMARCA once, and then we pick the best 100 beams, and then put it aside. Then run eMARCA again. Say, for example, eMARCA generated 250 beams. So we will add these 250 beams together with the 100 beams that we collected last time. Now we have 350 beams. We optimize using this optimization model, integer model, and then we do it again and again and again. So it will become slow for larger problems, but it does have this evolutionary aspect of it. And then we have the pricing part. So remember I mentioned that if we went for the exhaustive one, we just compare whether the beams has been generated or not, and see whether it is duplicated. But we don't actually have to check whether it is duplicated had we used pricing, so we can use the geo variables to help us, see whether the beam is worth adding into the pool. Although we do have one problem, it's because we don't have the optimal geo. So we solve the LP relaxation with a set of candidate beams once, right? Then you have all the geo variables here. But we don't have the geo variable corresponding to this constraint or this constraint. And the reason we don't have them is because we don't have the constraint. And the reason we don't have the constraint is because we don't have the columns to start with. So just like how some challenging issues in the world are being solved, we pretend that the problem does not exist. So we just remove the constraints and just pretend that we have a problem without the coloring. So we are only just solving the linear programming relaxation of the problem anyways. And the whole point is just to generate some columns. And given that a lot of the things are estimation anyways, for example, the gain pattern and all the rest of it, or even the losses and things like that. So they're just, estimations anyway. So what is the point of solving a problem to prove an optimality? So we just use the pricing to help us pick the best beams to add into the to the pool. So we can stop the pricing part when there is no more negative reduced columns, and then we solve the integer programming problem now with the coloring. So that's our column generation branches of algorithms. But even that is slow. So in the end, for the hardest problems, we just generate up to 500 beams and then that's it. So then we solve the integer programming model. So remember I mentioned that the STS-17 satellite has 200 spot beams. I thought that's already a lot, but future high-throughput satellites may have hundreds or even thousands of beams, I was told. So we tried to solve a problem with 400 beams with the smallest beam size possible. Anyways, so it is probably not so surprising that we can achieve much better percentage demand net. So the problem instances 11 and 12, so these are all the 5,000 users instances. So problem instances 11 and 12, the improvement is not so big. It's from here to here and here to here. So probably about 20%. So not so impressive, but for these 4 instances, we get big improvement with more beams. So more beams, more smaller beams are good. Actually, we also ran some other experiments with different beam sizes and a number of beams, and it turns out it is better to use smaller beams but more of them. Anyways, so this thing I think people might be asking is, oh, but the computation time is actually a lot less when you have 400 beams. But if you remember the integer programming model that I showed you earlier, it is absolutely expected because there's the NASA constraint. And the only thing that's different is that now you have 400 beams rather than 200 beams, for example. So the right-hand side is bigger. And of course, it's easier to get feasible solutions. So that's kind of like expected. Okay, so I think that's probably all. So thank you.